All right, let's do two more examples of sketching the graph of a derivative. So if they give us a function, it looks like this is f of x, and we want to graph the derivative of this function. We can think about the derivative as being the slope of my tangent line, the slope at any point. So I can go through this graph and figure out where I think, or estimate what I think the slope is. So if I'm going through this graph and I stop here, to me, this has a positive slope. Here, it has a positive slope. Here, it has a positive slope. Actually, isn't the slope the same this whole entire time? It doesn't curve at all. So it has the same slope. Would you say that the slope there is, I don't know, maybe a 1? A rise over run of 1 over 1? So I'm going to say that my slope is a 1 all the way through there. So my slope is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then all of a sudden, what happens with my slope? Doesn't it look like the slope then goes negative? And it looks like it's approximately a negative 1, doesn't it? So then my slope all of a sudden is a negative 1, negative 1, negative 1. And then it gets stopped. Do you remember what happens in our derivative at a sharp point? Yeah, our derivative doesn't exist, right? Because our slope changes so drastically, there is no derivative value there at that sharp point. So if I were graphing the derivative, remember the slope of my tangent line was 1 for a while. It was 1, 1, 1, 1, 1, 1, 1 until all of a sudden I got to that sharp point. Do you notice that I graphed the derivative up at 1 because that's approximately what the slope was, what the value of my derivative was? My slope was 1, 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 and then my slope didn't exist. So I'm going to signify that with an open circle. Because of that sharp turn, we talked about that in a previous video, sharp turns are where derivatives don't exist. So we don't have a value there for my derivative. And then all of a sudden, on the other side of x equals negative 2, what is the value of my derivative? What's the slope there? Didn't we say all of a sudden it was a negative 1? So then all of a sudden at negative 2, my slope is down here. Maybe I need to go a little bit higher to negative 1. It was down here at negative 1, negative 1, negative 1, negative 1. And then all of a sudden there's a gap, right? It jumps and there is no slope. There is no derivative. So I'm going to do another open circle on both sides. I have my sharp point where I don't have a derivative, and then I have that big old gap where I don't have a derivative. So again, my slope looks like it's going to be 1, 1, 1, 1, 1, 1, 1, 1, 1, and then there is going to be no derivative because of that sharp turn. And there is going to be no derivative, and then all of a sudden on the other side it drops to a negative 1 slope, negative 1 derivative, and then there's a big old gap, so there is no derivative. And then what happens? If I jump over this gap and I start to look at the value of my derivative, the slope of my tangent line, if I pick a point right here, isn't that slope pretty steep? It's a pretty high positive number. But then if you pick a number here, it's still positive, but it's less positive. And then if I pick a number here, it's still positive, but less positive, right? And so it starts off really positive, a high positive number. So if I want to go to graph that derivative, I need to start up here at a really high positive number. But then I want to get less positive, less positive, less positive, right? I was really positive, and then I was less positive. And then as I went less and less and less positive until it almost looks like I hit 0. So let's graph that. Let's graph the values of that slope or the derivative. It starts off really positive, and then it goes less positive, less positive, less positive until it almost looks like it goes to 0, something like that. So this would be the graph of the derivative. The blue is the graph of my original. The purple is the graph of the derivative. Whew, a little bit tricky, right? All right, why don't you try this one? Example number 4 actually gives you two graphs. One of the graphs is the original f function. The other graph is its derivative, f prime. See if you can decide which one of these lines, which one of these graphs is the original, f of x, and which one is its derivative. Okay, so I'm going to try probably by looking at one of them, just pick one, and figuring out where the slopes equal 0 first. That's probably the easiest step. So I'm going to start with the blue. I don't know, as it's y1. And then as I'm following, I know the slope is negative, it's negative, it's negative, and then all of a sudden it's 0 right here, right? So that's a significant point on my graph. My slope of my tangent line is 0 right there. So if I were graphing the derivative, then I know that my derivative would be 0 right there, and it would touch the x-axis. On the other side of that 0, my slope looks like it's positive, and then all of a sudden it looks like it hits 0 again, doesn't it? So it looks like it's positive, 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 and then it hits 0 again at that point. So I'm going to go down to 0 because I know that that's what my derivative is going to be at that point, the slope of my tangent line. On the other side, it looks like the slope is negative. It gets more negative, it gets less negative until it hits 0 again right there. So I know that the derivative value here is also 0. So I'm going to plot that. On the other side of that 0, it looks like my derivative or my slope is positive. So if I go through and I pick those important characteristics where the derivative is 0, I know that it's 0 here, I know that it's 0 here, I know that it's 0 here. Those are all the places where I have a horizontal tangent line, where it's flat, horizontal, right? The slope is 0. So I can go through and plot those 3 zeros. Then I can look at each interval. What's happening before the zeros? So in this one, what's happening over here in this interval on the other side of x equals 0? Well, in that blue graph, we just said that our slope was negative and then it got less negative until it hit 0. So if I were to graph that, I'm going to graph negative values and then they got less negative until it hit 0. So it would look something like that. Now, in between the two zeros, what was the value of my slope? Well, it looked like it was positive, and then it went less positive until it hit 0. So it was positive, it went less positive until it hit 0. Whoops. On the other side, it was negative, more negative, and then less negative until it hit 0. So let's graph that. Here, I went negative, I went more negative, I went less negative until I hit 0. So it would look something like that. On the other side, where it hit 0, my graph has a positive slope. So it's positive, and then it looks like it maybe gets less positive. So it looks like y1 is actually our original function. It happened to be that that's my original function, and it just worked out, which means that y2 is really the derivative of that function. It's not always going to be the case. They might switch it up on you, but that was one way to tell. I just picked one of the lines. I figured out first where the slopes were 0, where I had a horizontal tangent, and then I looked at each interval in between those zeros. Was my slope positive or was my slope negative? If my slope on my tangent line is positive, then I know I'm going to graph my derivative above the x-axis because it has positive values. If my slopes are negative, then I know that I'm going to graph the derivative below the x-axis because that has negative values. And then I can go from there and see if it matches the graph. Make sure you practice those. Those are a little bit tricky. You'll have those on your homework and your exam, so make sure you practice graphing a derivative. I know sometimes on my math lab they might give you multiple choice, but it might be helpful to sketch the graph on a piece of paper and graph it yourself first, and then check your answer with the figures that they provide you.